So I've made some version of this video before, both separately for homology and cohomology, and I never liked that I felt like I never really gave the full description that I wanted to. So I'm making this video again for like the third time. Um, but I want to answer what is cohomology, why is cohomology or homology. These are kind of the same thing, and I'm going to link some of those other videos. I'm going to refer to them. I'll also refer to some other people's videos. But one thing I want to clear up right off the bat that maybe a misconception, not quite a misconception, but an idea that a lot of people have about homology. When they first hear about it, they have this idea that homology is about counting the holes in some topological shape, right? So like this torus has one hole. Same if you removed a point from the complex plane, or homotopy versus homology in terms of like the coffee mug. God, I can't draw a coffee mug, but imagine a coffee mug. You know what I mean. Something like this, right? And that's not entirely wrong, right? Classically, so classically, homology, homological algebra, this did arise from trying to find some algebraic way to classify topological shapes, and as sort of a crude fundamental thing is that you can think about homology groups as quantifying how many holes that some shape has. However, homology, homological algebra, and cohomology is so much more general than topological spaces. It's really, in its broadest form, is something to do with algebra. And in fact, I claim that it is entirely encapsulated by the idea of a map not being surjective. So I've said time and time again, what is cohomology? It's the measurement of the failure of a map to be surjective. And I want to explain what I mean by that. And the point is that homology in this topological sense is just a very, very, very special case of homology or cohomology in the general algebraic sense. And in particular, it is, again, a very, very special case of the measurement of a map, of its failure to be surjective. And really, that's what is giving rise to some sort of counting of holes here. Okay, so what do I mean by that? So bear with me for a moment. I'm going to give an abstract definition, and then we are going to specialize. We're going to look at a whole bunch of special cases, and we're going to see that it recovers things you probably already know about. So these ideas work in great generality to be as fancy as possible. Sort of the main context for which these ideas I'm about to talk about hold are in an abelian category. If that means nothing to you, do not worry about it. The objects and the maps I'm going to talk about in this video, you can either think of as being abelian groups, or you could think of them as vector spaces. If either one of those things are comfortable to you, then great. That's the thing I want you to think about. So the first definition that we need to talk about this, remember, the topological stuff is going to come out as a special case of this. So the first definition that we need is the notion of a chain complex. So a chain complex is going to be some potentially infinite sequence of objects, again, abelian groups, vector spaces, whatever, with maps in between them satisfying some conditions. So oftentimes, if the indices are decreasing, we can either write them with decreasing indices, or we can write them with increasing indices. And maybe sometimes, maybe when the indices are increasing, they sometimes get written upstairs. It doesn't really matter. And okay, there's more for me to say about this. This isn't technically the whole story, but in some sense, what is the difference between homology and cohomology? It's just the choice of indexing. Okay. Kind of at a formal level, that's true. In practice, there's maybe more to it. Cohomology is really, you should think of it as some sort of dual space to homology or something. And okay. But really, everything I'm going to say here in terms of failures of maps or surjectivity, it really does apply to both homology and cohomology, and is basically just this difference of indexing. Okay. So just out of a slight preference, I'm going to use the cohomological indexing, the increasing indexing. Okay. So what is it? I have some sequence, right? Potentially, it could be infinitely long, of some objects like abelian groups and maps between them. So maps meaning like homomorphisms of abelian groups, or if you're thinking about vector spaces, these are linear transformations. So it's not just that. It's not just the sequence, but I'm also going to ask that the composition of any two of these, of any two successive maps, so di composed with di plus 1 is going to be the zero map. So another way that we say this is that the image of di is going to be contained in the kernel of di plus 1. Okay, that's what makes it a complex. And I'm going to give you one more definition before we jump into some examples. Here it is, the cohomology. This is it. This is the entire theory right here in a single statement. The cohomology of this complex, so this is a shorthand for this entire potentially infinite string. The ith cohomology of this complex is, so remember, this is some abelian group. This is some abelian group, or vector space, if you like. It's the kernel modulo the image. And this makes sense precisely because we said, well, the requirement to call this thing a complex means that the image is contained in the kernel. So we have to be able to mod out by it. And this is what I mean by it all comes down to a measurement of surjectivity of some map. Because the homology will be 0 if and only if the image of di is equal to the kernel of di plus 1. In other words, it will be 0 if and only if the map from ci over to the kernel of di plus 1 is surjective. Okay. Who cares? Why? Why is this homology? What does this have to do with topological spaces? Okay, we'll get into that to a second. But why is this measuring the failure of surjectivity? Well, trivial homology means surjective map. The bigger the homology group is, right, the further away it is from 0, this means the further away this image is from being the entirety of the kernel. So the bigger the homology, the further away this map is from being surjective. And this is it. This covers all of it. Group cohomology, sheaf cohomology, blah, 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 DRAM cohomology. Okay, there's other crazier cohomologies which are defined like maybe slightly fancier, but like this is the fundamental idea. So why? Let's look at some examples. This is all very abstract and heady. Let's look at some examples. Why would anyone want to consider this? So of course, being mathematicians, we should think, what is the simplest possible example? Well, what is the simplest possible vector space or abelian group, whatever, was normally the 0 object, right? The vector space with one element being the 0 vector, or the abelian group with one element being the identity element. So you could imagine an entire chain, right, of groups going on forever. They're all 0. Why would you want to consider it? Oh, well, I wouldn't. I mean, it's about as important as 0 is, right? Which is important, but it's like most of the time we don't think about this. And so what are the maps that would go in between these? Well, all of these just have to be the identity map, right? There's nothing else to send it to. All of these things have one object in them. Okay. And so what is this a chain complex? Well, let's see. If we look at any of these maps, right? The identity map, right? This is we just got one thing with like the identity element in it, and it's getting mapped to the identity element. So the image of each one of these identity maps is just the thing containing the identity, and of course the kernel of each one of these identity maps is just the identity. So in this example, it's sort of, yes, it's a complex. And not only is it a complex, but the image and the kernel are equal. So that would mean that everywhere in this complex, right, maybe I'll call it 0 dot for the 0 complex, the homology is trivial. The homology is trivial. By the way, when we talk about exact sequences, this is all we mean. We say the sequence is exact at some particular position if the image and the kernel are equal. In other words, if the homology is 0. Okay, let's see if we can find a less trivial example. So let's look at, so we'll have 0 into some G. Okay, I'm going to be thinking about abelian groups. You can keep thinking about vector spaces if you want. So let's allow possibly one thing that's not 0. And then I'm going to stop drawing the dots. We can imagine that there's zeros infinitely left and right, but they really have no bearing on what's going on here. And so, okay, what does it mean for this thing to be a complex? Well, let's think about, what could this first map possibly be? Well, this is the thing with one element, right? Say abelian group with one element. There's only one map out of it, right? Because there's only one thing in, right? The trivial group is just the group with an identity element. We have to send that identity element somewhere, but we don't have a choice, right? Group homomorphism has to send identity to the identity. So there's just one map, and we call it the 0 map, right? Because it just maps the identity to the identity. Okay. It maps everything in the first group to the identity. Okay, what about the second map? What could it possibly be? Well, again, everything in G, there's only one thing in here. Everything in G must get mapped to that one thing. Because there's only one thing for everything to get sent to. So that is also the 0 map. Okay, so here we're forced. We don't have a choice. We don't have a choice for what these maps could possibly be. Is this a complex? Well, we have to check. Is the image of the first 0 map? Well, we know, again, that is just going to be the identity element of G. And of course, the identity element, well, of course that's in the kernel. Of course that's in the kernel of this second 0 map. Maybe I should even label them. I'll go 0 map 1 and 0 map 2, right? So is the image of 0 map 1 in the kernel of 0 map 2? Yes. Yes. So we were forced, these maps were forced upon us. We were able to check these things. Okay. So this is definitely a complex. And, well, let's think about what's happening. What is the homology at G? The homology at G. So I guess the way I've labeled this, it seems like G is in the 2 position. So whatever. Our complex, the homology, is going to be what? It's going to be the kernel of the second 0 map modulo the image of the first 0 map. But the image of the first 0 map is just the identity subgroup, the trivial subgroup of G. And the kernel of the second 0 map is everything, right? The second 0 map sends everything to 0. So here we get G. So in other words, this is just G again, right? So the homology just recovers G. And you might say, who cares? Why? We did all this work, all these fancy things, and what? We've recovered the thing that we started with? Yes, but again, I'm slowly trying to build up for you all these explicit examples of homology and what they mean. And pretty soon we're going to start recovering things that you might actually care about. Which again, you might say, oh, isn't there simpler ways to do it? But yes, we're slowly building up to the general idea. Okay, And so here, in this case, what does homology tell us? Well, the homology in this case would be 0 if and only if the group G is 0, right? Because the group G is isomorphic to the homology. Okay, so in this most basic non-trivial example, what is the homology measuring? It's measuring how far your group is away from being the trivial group, basically, right? The larger, say in cardinality, if you will, your homology group is, the further away your group is from being 0. So it sort of measures something. And how is it measuring that? Well, it's measuring it by seeing how far away is the 0 map into your group away from being a surjection onto the kernel of the 0 map, right? So again, fundamentally, it is all about measuring how far some map is away from being a surjection. Okay, let's now look at a step up again. So what if we had two terms next to each other that were non-trivial? So we have H, we have G, we have H, we have 0. Again, this has to be the 0 map, and this has to be the 0 map. There's no other choice. There's no other choice. Same argument as before. Now we could put some homomorphism here in the middle. What would it take to make this thing a complex? Well, the image of 0, again, that's just going to be the trivial subgroup of G. So I'm going to start abusively writing all of these things as 0. And so, of course, right, that's just the group containing the identity of G. Of course, that is contained in the kernel of F. Great. And let's look at, now, what about the image of F? Well, the image of F is undoubtedly contained in H. But remember, this 0 map here, it sends everything in H to 0. So the entirety of H is the kernel of this other 0 map. And so great, this is a complex. And then the other, if we had more zeros on either end, well, it's the same argument as before. So great, actually, for any group homomorphism, this is a complex. It almost seems so far like being a complex is no restriction at all. So, okay, what does the homology mean now? What does the homology mean? So let's look at, I don't know, I'll call this, this will be position 0, say this will be position 1, position 2, and position 3. So, this is our complex, C dot. So what is the first cohomology of our complex at C naught? Well, by definition, it is the kernel modulo the image of the 0 map. So in other words, well, the image of the 0 map, again, is 0. So this is just going to be, it's just going to be the kernel of F, right? Because this bottom thing is trivial. We're modding out by nothing, essentially. So what does that mean? Well, how do we interpret what the homology group is telling us? Well, the homology group is trivial if and only if the kernel is trivial. But the kernel is trivial if and only if the map is injective. So here's an interesting thought. The first homology of this complex is measuring how far F is from being injective, right? The bigger the first homology group is, the bigger the kernel of F is, which means the less injective F is. But wasn't I telling you that this was all fundamentally just about the lack of surjectivity of some map? But it is, right? Because the definition of the first homology group is what? It's this, right? And so, again, it is measuring the failure. How far does the 0 map fail from being a surjection onto the kernel? If it doesn't fail, if it is a surjection, then the first homology group is trivial, and so the kernel is trivial, and so it's injective. So we're measuring injectivity with surjectivity. Fascinating. Okay. What about the other term of the sequence? So what if we looked at the second cohomology of our sequence? Well, that is the kernel of this second zero map modulo the image of f. And so what? Well, the kernel is just h. So that's everything. And so now this is the image of h modulo this is h modulo the image of f. And now this is more in line with how we normally think about surjectivity, right? Now this is telling us about the surjectivity of f. So this homology group will be trivial if and only if the image of f is equal to h. So in other words, the second homology group of this particular complex is measuring how far away f is from being a surjection. And here it's quite more a literal interpretation, right? So now we're seeing an example in this basic example. We're starting to see how complexes and homology recover things that we care about. In algebra, we care about things like images and kernels and surjectivity and injectivity. And so here the homology is giving us some way of measuring injectivity or surjectivity and how far we deviate from those things. Okay, so what could a three-term sequence possibly tell us? Well, let's start writing it out. So we'll have f and well, maybe I should call these maps. I'll call this map G, and I'll call this map H, K. So now I have a sequence with three terms. So by the same arguments that we've done before, we know that the kernel of 0 is definitely, or sorry, the image of 0. The image of 0 is contained in the kernel of G. And we know that the image of H has to be contained in the kernel of 0. Those are things that were just forced on us. That we weren't even asking this to be a complex yet. Now now here is a case where we're not necessarily forced to have a complex, right? Because in order for this to be a complex, we would also need that the image of G is contained in the kernel of H. That doesn't have to happen, right? I mean, if you choose G, H, and K to just be some random groups, these first two things have to happen, but you could just pick some random groups and just pick the image of G to just well, I guess I can't totally miss the kernel, because of course something's going to map to the 0 element, but there's no reason in general that the image would have to be contained in the kernel in general. But there is if we want this to be a complex, right? So if we want this to satisfy the definition of complex, which we need to even make sense of homology, then we're going to ask that this condition is satisfied as well. So what that means is when we apply these maps, right, nothing that started off in G is going to survive into K, right? Because this condition, remember, is equivalent to saying that H composed with G is the 0 map. So H composed with G, right, that goes from G to K. So if you compose through these maps, nothing in G would survive to K because it would be the 0 map. Okay. So what does the homology here mean? Well, we already know that by the same arguments we've provided above, we already know that the homology at the position where G is measures the injectivity of H. We also know that the homology in the position of where K is measures the surjectivity of H. What the homology at the middle position is, well, it is exactly, so I don't know what to call this. This is the middle position. Maybe I'll call this -1, 0, 1, 2, -2. So this is my complex. And so the coHomology here, the indexing doesn't matter. It's not so important. But this is, by definition, the kernel of H modulo the image of G. So, again, it is just measuring the failure of G to be a surjection between big G and the kernel of H. It's measuring, another way to put it, using terminology we just recently learned, it's measuring the failure of exactness at the sequence. What does that really mean in this case? Well, you should probably go look at my series on group coHomology, or rather starting with how to invent semi-direct products. It should be a great follow-up to this video to get a better sense of why short exact sequences really tell us how to build a group from two smaller already existing groups. Interrupt myself here to actually explain an important part of when we have a complex like this with three terms, and what happens when first, what if it is exact, which is the same thing as saying that the homology or coHomology is trivial everywhere, which is the same thing as saying that the image of each map is equal to the kernel of the map that follows it. Well, first off, irrespective of those things, because H is surjective, by the first isomorphism theorem, we know that K is isomorphic to H modulo the kernel of little h, right? So now what that means is if we have exactness, right? We don't always have exactness, but if we have exactness, then what we have is that this is the same thing as saying H modulo the image of G, right? And again, if we have exactness, this means that little g is injective. So that means that G is an isomorphism onto its image, right? It's an isomorphism onto the image of little g here. So that means that basically we have a copy of the group G that lives inside the group H. And we recover K exactly by killing that copy of G that lives inside there. It's exactly the kernel. So H is sort of precisely fit together from G and K with no overlap. But what if it's not exact? Well, if it's not exact, then we merely have that the image of G is only contained in the kernel of H. And so that means, though, that we will get a map from H mod the image onto here. We should get a surjective map simply by quotienting yet even further down to the kernel, right? And so in this case, it would tell us, so here the first isomorphism theorem still says that, yes, if we just kill the kernel, we get exactly K. But now H mod the image of G, right? If we kill the copy of G, we don't exactly recover K. And that's what I mean by there being no overlap. There's like still a little bit of stuff left over. There could be a kernel here to this projection. So that's just an extra interpretation that I wanted to throw in here. And the thing is, we can keep going. So where do sequences of four terms? Now it becomes a little bit more complicated to explain exactly what the relationships are. But at the end of the day, like I said before, it's all about measuring the failure of some map to be surjective. Let me just give you one example from group theory in general of a short exact sequence with four terms. So if you have a group, remember that each element of the group determines an automorphism of your group by conjugation. So each G in your group determines a map from your group to itself where you send X to X conjugated by G. So we get a homomorphism. In fact, this defines a homomorphism from G to its own automorphism group. The kernel of that homomorphism is the center of G, because if G was in the center, then these elements would commute and this would just be the identity map. So that doesn't have to happen in general, but certainly the center of your group is the kernel. And then finally, it does not have to be the case that every automorphism of your group comes from an inner automorphism, although famously for most of the symmetric groups it is. And so if we simply put the quotient here of aught G, and maybe I'll call this map alpha modulo the image of alpha, now we get a surjection here. And so this is a very famous, very important exact sequence with 4 terms, and this holds for any group. And so, of course, we can consider what the homology or cohomology of all of this means. Okay, so that in general is what homology and cohomology is. Oh my gosh, I forgot to tell you a very important thing. So let's go back to this 2-term sequence for a moment. By the way, if this whole sequence is exact, what does that mean? The important thing I forgot to tell you, you could have pieced this together on your own. Of course, the homology here measures injectivity of F. The homology here measures the surjectivity. So if all the homology is trivial, this means that F is an isomorphism, by the way. Okay, maybe not such a huge deal, but I forgot that. But one of the things we did want to talk about here was, what does this have to do with algebraic topology? So all of you back at the beginning of the video, right, I promised that this had something to do with algebraic topology, and I said that this was a very, very special case, right? So what that case is so homology has something to do with chain complexes. So what we do in algebraic topology is we come up with a chain complex. And again, this works for sheaves and de Rham cohomology, singular cohomology, blah, 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 the whole works. What we do is we come up with these chain complexes, these algebraic structures that measure some part of our topological spaces. So these could be groups or vector spaces, depending on the exact flavor of this that you're doing. But this is exactly what the homology of a space is we come up, there's this sort of sequence. I'll let you go read up on the particulars of how we, construct these actual sequences, but we come up with these sequences built out of essentially continuous maps into your topological space, because what else would they be? Well, it's slightly different for different kinds of cohomology and whatnot. But we build a sequence out of some relations to our topological space, and the homology of your topological space, perhaps I should use lower indices if I'm talking about homology, the homology of your topological space is literally just the homology of the sequence in the way that we've defined it. There's some map, and you're taking the kernel of one of these maps modulo the image of the map that came before. And that's all there is to it. Well, if you follow this channel after this video, I can guarantee you're going to see me yapping a whole lot more about homology, cohomology, and stuff to do with groups and inner and outer automorphisms. So with that being said, QED.